We are now ready to bring the language of statistical estimation to the SparseLand model. Statistical estimation makes sense only when our signals are defined by a clear random generator. So let's describe the details of our signal source. The matrix D, the dictionary, is assumed to be fixed and known. The representation alpha is created randomly by first choosing the support. We shall assume that for each entry, a coin is flipped to decide whether it is non-zero with probability p. Given the support, we randomly draw the non-zero values in these locations. We shall assume that these are given as IID, zero mean Gaussians. Now that alpha is created, it is multiplied by d and we get the signal x. In our notations, ds is a submatrix of D containing only the used atoms, and alpha s is the non-zero part of alpha. The bottom line to all this story is this: the probabilities of p of alpha or p of x are clearly defined. Given the signal x that has been generated this way, we now assume that it is contaminated by white additive Gaussian noise and we obtain z. The conditional probability of z given x is a simple shifted Gaussian as shown here. This implies that various conditional probabilities are now available to us. These include p of alpha given z or p of s, the support, given z. We are now ready to bring in statistical estimators. We have these two posteriors and thus we could do things such as applying map or MMSE. In applying map, we could search for the most probable alpha given the noisy signal z, or better yet, search for the most probable support s to explain this data. In the MMSE case, we could evaluate the conditional mean of alpha given z. A third branch of activity that we can employ is to investigate the oracle estimator. The oracle is a machine that knows the support, and thus its estimation task of finding the non-zero values is much easier. Why should we bother with the oracle? Well, because of two important reasons. First, we will see that it is a building block in the other two estimators. Secondly, it will give us a reference to compare with when evaluating how good our estimations are. Let's start with the oracle, because its analysis is the easiest. The oracle works with a posterior probability of alpha given z and s. Knowing s means that we know where the zeros are in alpha, and so our estimation focuses only on the non-zero part, alpha s. Using the base rule, we get this alternative expression. Who is p of z given alpha s? This is exactly the Gaussian distribution of the noise. Who is p of alpha s? This is yet another Gaussian that describes the distribution of the non-zeros. So we can write the oracle's posterior as the multiplication of the two, and the denominator serves only as normalization. This PDF is Gaussian as well, and its peak or mean are both the map and MMSE estimations of alpha s. Here is the expression we get for this estimation. Observe the notations for hs and qs. So to summarize, this formula is both the map and the MMSE in the oracle case, since its PDF is symmetric. By the way, what if we are after the estimation of x and not alpha s? All we need to do is to multiply the estimated alpha s by ds. Let's derive now the map estimation of the support. We do so by maximizing the posterior, the probability of s given z. Again, we use the base rule in order to simplify the analysis. How can we get p of z given s? Actually, we cannot do this directly. But we could integrate the conditional probability of z given alpha and s over the entire alphas referring to this support, a trick known as marginalization. Here it is, and I will not burden you with the fine details here. We end up with this expression that uses only known ingredients. The reason we were able to get to a closed form expression comes from the fact that inside this integral, we get a pure Gaussian distribution for which the integration is known. What about p of s? This is easy, as we have defined the probability of each entry to be non-zero as p, and thus 1 minus p for the zeros. Therefore, merging everything together, here is the expression that map aims to maximize. Note that the constant normalizing all this distribution is of no importance to us. Let's talk about the implications of the result we just got. The estimated support is the one maximizing this expression. So numerically, we should sweep through all the possible supports and search for the one that maximizes this function. Having found this support, the estimate of alpha itself should be the oracle over this found support. I'm sure you realize that evaluating this map is an impossible task due to the exponential number of possible supports. So what do? We turn to approximations, as we will discuss later. I'm sure you don't see it now, but I'll mention it anyhow. OMP is a way to approximate the solution of the above problem. Let's move to derive the MMSE estimate. This will be the expected value of alpha given z, and here again we use the marginalization trick, but this time by summing over all the supports, thus getting this big summation. Now take a closer look at the expression we just got. The expected value of alpha given z and s is nothing but the oracle that refers to the support s. Also, the probability of s given z is exactly the expression we just derived for the map. So everything is known to us here, and we can turn to compute this estimation. It will be a weighted average of many oracle estimates, each having a different support and each weighted by the probability of this support to explain z. Does this ring a bell? Do you remember that we averaged a group of sparse representations and got a much better result? We just derived the MMSE, and it is given by a weighted average of many oracles. So the best estimator in terms of the L2 error for a signal that emerges from SparseLand is not sparse at all. Is this a contradiction of any sort to SparseLand? No, not at all. We do have to note that, just like the map, in general we cannot evaluate this estimator due to the impossible number of supports we should cover. Thus, just as before, we will need an approximation. Can you guess which algorithm could be considered as a good approximation for this estimator? This is the next topic on our agenda.